Hello and welcome to our next pre-lab video. This is the pre-lab video for virtual lab number 5, free energy. And this lab is set up in kind of an interesting way. It's a virtual lab and it piggybacks very well off of what we were doing last week. So let me start by showing you what I've been looking at. And so if we get into the assignment here, the full name of the assignment is free energy and temperature. And so you think about what we did in the reaction spontaneity lab from last week. We were looking at the relationship between enthalpy, entropy, temperature, and spontaneity. And one way that we can do this, and if you recall, some of you I had conversations with about the idea of a flipping temperature. So for those of you that weren't in those conversations, let me quickly just explain that when a reaction is temperature dependent, that is delta S and delta H have the same sign, then there is a temperature at which the reaction flips from spontaneous to non-spontaneous, or vice versa. And so what we're looking at in this particular case is a way to do that kind of determination only graphically. And so the graph that we're going to create is going to put one axis as delta H, or excuse me, one axis as delta G, and one axis as the temperature. And what we will see is that the value of delta G is going to hit a spot where it crosses this line and flips from being a negative value to a positive value. And so I've actually got this put in the wrong place. The line goes like this. So up here on this half of the x-axis, delta G is positive and the reaction is non-spontaneous. Down here, delta G is negative and the reaction is in fact spontaneous. And that place where it crosses that x-axis, that is in fact the flipping temperature. Now, this flipping temperature has a special designation associated with it. Where the graph crosses the x-axis, that is the flipping temperature. At this exact temperature, the system is at equilibrium. And so what that means is that when we're at that spot, our delta G value is equal to 0. And so instead of having the reaction be spontaneous or non-spontaneous, what we see is that the reaction is actually reversible, where both reactions, the forward and the reverse, both are occurring at the same time, at the same rate. And so at that spot, the reaction is neither spontaneous or non-spontaneous. It's kind of both at the same time, because both reactions, the forward and the reverse, are occurring at the same time and the same rate. So let's get into what this actually means as far as the procedure is concerned for this lab. This is a simulation lab, so you will be doing a simulation. The analyzer we are using is this one. Again, I would strongly suggest doing a control click so that you do not accidentally navigate your way out of lab archives. But what you'll see is that here I've got my chem reacts. And what I want to do is I'm going to do 5 different experiments. The 5 different experiments are given to me in the data and results section. They start with bromine here. How you get to that is if you go to reaction selector, which is right here. The first reaction that you want to do is a phase change. The phase change that you're investigating is the bromine evaporation phase change. So I'm going to click on that and I'm going to hit continue. And then what this is going to do, and so again, I'm going to advocate doing a split screen kind of model here. What this is going to do is I want to set my parameters. So I'm going to start at 200 Kelvin, pressure factor of 1, and I'm going to hit run reaction. Takes a couple of seconds for the simulator to do the analysis, but it'll spit out 3 data points for us. And those data points are going to be what we record here in the data and results section. Here we're going to record that for 200 degrees Kelvin, we had a delta H value of 35.93 kilojoules, a delta S value of 0.11 kilojoules, and a delta G value of 13.68 kilojoules. Your remaining tasks for this particular reaction are to do the reaction at 200 degrees, the reaction at 700 degrees. So all you have to do is change the temperature, hit run reaction again. It'll spit out new values for you in terms of entropy, delta G, and delta H. And you'll record those down here. And then you're going to have to pick up about 25 points in between. So if you're going for, you're going to end up graphing this. So if you go for the points, try to pick a good spread from 200 to 700. Pick up a lot of data points kind of in between so that your data are going to be very easy to see the trends. You don't want to pick 200, 201, 202, 203, 204, 700. Spread them out. You don't have to spread them out exactly, but spread them out. Make sure that you get 300, 400, 500, 600. Make sure that you get all the 50 values. Make sure that you get some of the values in between. And by the time you know it, you'll run out of data points to collect. After you've gotten all those data points, you're going to go back to reaction selector, and you're going to pick up the second reaction, which is also a phase change. So I hit start, phase change. Here I'm going for the evaporation of water, continue, and then repeat the entire process again. 200 degrees, run, 700 degrees, or excuse me, in this case, 2000 degrees, run, all the points in between. The third one is also a phase change, aluminum liquid to gas. And then the fourth and fifth ones, you've got combustion reaction here. So you're going to go to reaction selector, start, and let's try, no, not combustion, synthesis. no. Reaction 4 is a synthesis reaction, and then reaction 5 you have to enter manually. So, okay, here's reaction 4, continue, and then for reaction 5, you'll have to input it manually. Reaction 5 is hydrogen, the oxidation of hydrogen by carbon dioxide. And so you can put that in. It's a little bit more arduous to do, but you can do it reactant by reactant. H2. So find H2 gas and CO2 gas, make H2O gas, and CO. You have to dig a little bit here, but there it is, gas. Again, set the same kinds of parameters, run the reaction, collect all your data. In the end, you're going to make graphs for all 5 reactions. You're going to make a graph of delta H versus time, delta S versus time, delta G versus time on the same set of coordinates. So you're going to make 5 graphs in total. Each graph is going to have 3 trend lines on it. And then for the post lab, you're basically interpreting your graphs. How does the enthalpy change with temperature? How does the entropy change with temperature? What is the x-intercept for each graph? So for delta G, so what is that flipping temperature for the 5? Are they endothermic or exothermic? You know, compare and contrast the plots to each other. So that's it for this particular video. Kind of a short one this week, but pretty straightforward and kind of fits in well with what we were doing last week. Of course, if you have any questions, feel free to reach out to me and send me an email or a reminder that this pre-lab assignment is going to be due on Monday night. So don't delay in going and getting started on that. Have a great day.